panel.
Well, so I'm John Kohl, the PI on what we call the Coronal Physics Investigator experiment for the International Space Station. That's a mission of opportunity. And so I guess that makes us a small, complete mission. The general idea is to do a high-resolution spectroscopy of the extended solar corona, and by that I mean above a few tenths of a radius from the limb of the sun, where you can no longer use a conventional instrument because of the extreme stray light suppression requirements. Okay, so thought I'd try to get into your storytelling mode a little bit and tell you a little bit about the history. The first observations of the ultraviolet extended corona were made on the 7th of March, 1970, when an objective grating spectrograph flew into the umbra of a natural solar eclipse on an Aerobee sounding rocket flown from Wallops Island, Virginia. And some very interesting results that came from that. The brightest line was the neutral hydrogen Lyman Alpha line, which no one expected to see in a 1 million degree plasma. But it turned out that the bright Lyman Alpha light from the solar disk would resonantly scatter with the small 1 part in 10 to the 5 protons that had an attached electron and cause this very bright Lyman Alpha radiation. Well, this excited a lot of people. We realized you could measure outflow velocity that way by doing something called Doppler dimming. And I was a young guy. I was a research associate at Harvard College Observatory, and they asked me to try to figure out how you could do this without a natural eclipse. So I came up with an instrument design idea. I added a high-resolution spectrometer because I thought we wanted to measure line profiles. We did a series of rocket flights. First one was in 1979. It proved it would work. Then we did a series of Spartan flights. We had 4 deployed flights on Spartan, 2-day missions. And then this all sort of was the foundation for something called UVCS SOHO, which is still operating. It was launched in 1995. And we measured properties of coronal protons, ions, and electrons from 1.5 to 10 solar radii, and pretty much from 1.5 to 5 with a few exceptions. There were some really nice things that came out of this. We were really delighted with the way it went. And probably the most well-known one is that in coronal holes we discovered strong preferential heating of O5 plus and magnesium 9 plus ions in the fast solar wind. And these were not isotropic temperatures. There was very pronounced anisotropy, with the temperature perpendicular to the magnetic field being much, much higher than the temperature along the magnetic field. Also found preferential acceleration of the ions. So the O5 plus was going out faster than the protons in the primary plasma. And all of this created quite a stir in the theoretical community and rekindled the idea that maybe the fast solar wind is being produced by waves, the high-frequency MHD waves or ion cyclotron waves that are accelerating the plasma with something called ion cyclotron resonance. Yep. So, So the CPI experiment, I think I want to back up here, is a next generation ultraviolet coronal spectrometer, and it has about 100 times the sensitivity of UVCS, depending on the height and the ion you're looking at and so on, but that's a good general number. And the much broader wavelength range, 25.7 nanometers to 126 nanometers. And the primary goal of CPI is to determine the physical processes that heat and accelerate both the minor ion plasma and the primary proton-electron helium plasma in both high-speed solar wind streams and slow-speed streams. And that gets broken down into 4 objectives that are listed here. I don't really have time to go through those. And because of this high sensitivity, CPI will observe many spectral lines never before observed in coronal holes above 1.4 solar radii. And this we believe is the key to trying to unravel this mystery of what the physical processes are that accelerate the solar wind. CPI science team, I'll just go quickly through that. In addition to myself, I want to highlight these two former graduate students of mine, Harvard graduate students, PhD students, now professors at the University of Montana, project scientist and the instrument scientist. The Theoretical Physics Brain Trust is Steve Cranmer, John Raymond, and Odd Van Bellehoyn from SAO, and Ben Chandran, Terry Forbes, and Phil Eisenberg from UNH. And then we have some of the management and engineering people listed here, not all of them, but Tim Norton's the project manager, he's sitting over there. Paul Cucchiaro is the payload manager for L3Com, the industrial partner that will be building the instrument. Brian Ryder is the system engineer for L3, and we have a senior scientist, Alexander Panasiuk from SAO, who will do what you call, I guess we'd call it the mission software manager and science operations manager. How am I doing? 2 minutes. Okay. This is sort of a cartoon of the instrument here, and we're on the space station, showing over here on the Columbus SOS site. The sun flies by every 90 minutes. It takes about 60 minutes to fly across the sky, so you have to have a pointing system, gimbal's pointing system, to track it and also to lock onto the region of interest that you're trying to observe. This is a internally occluded coronagraph makes an image of the corona here and then goes through a spectrograph to get the high resolution. So